In question 1, we're given f of x here and we are asked to express it in partial fraction form. So we're looking at 5x plus 10 over 1 minus x times 2 plus 3x. Well, we will set this being equal to a constant a over 1 minus x plus another constant b over 2 plus 3x. Obviously, the LCM here is the 1 minus x, 2 plus 3x. So if I multiply throughout by this LCM, we get that 5x plus 10 is equal to a times 2 plus 3x plus b times 1 minus x. Now this statement here, it's an identity, so it holds true for all values of x. So obviously we set x to be 1. This will make this bracket 0 and will allow us to find a. So let's set x to be 1, which leads to 5 times 1 plus 10 being equal to a times 2 plus 3 times 1. So we're looking at 15 being equal to 5a, and therefore a is 3. Now another nice value of x will be the value that will make 2 plus 3x being equal to 0, which leads to x being minus 2 over 3. So let's set x to be minus 2 over 3, and we arrive at 5 times minus 2 over 3 plus 10 being equal to b times 1 minus the negative 2 over 3. So we get that 20 over 3 is equal to 5b over 3, and obviously this makes b to be 4, and the only thing missing is to write that down, the partial fraction decomposition. So we're looking at 5x plus 10 over the 1 minus x times 2 plus 3x being equal to 3 over 1 minus x plus 4 over 2 plus 3x. In part B, we're asked to find in ascending powers of x up to determine x squared the binomial series expansion of f of x, giving each coefficient as a simplified fraction. So starting with f of x, we're looking at 3 over 1 minus x plus 4 over 2 plus 3x, which I will write as 3 times 1 minus x to the minus 1 plus 4 times 2 plus 3x to the minus 1. Now, in order to proceed with the binomial expansion, I always need to be in the form of 1 plus or 1 minus something to the power of n. Obviously, this satisfies this particular form. However, the 2 plus 3x does not. So we're looking at 3 times 1 minus x to the minus 1 plus 4. And I'm factoring out the 2, and it inherits the power of negative 1. And within the bracket, I'm dividing everything by 2. So we're looking at 1 plus 3x over 2 to the power of negative 1. So we're looking at 3, and we expand using the binomial expansion. We've got 1 plus the power of negative 1 times the negative x plus the power of negative 1. We deduct 1, we go to negative 2 over 2 factorial times the negative x squared plus dot dot dot. And then we've got 4 times 2 to the negative 1, which is simply 2. And the binomial expansion of 1 plus 3x over 2 raised to the negative 1 will be 1 plus the negative 1 times the 3x over 2 plus the negative 1 times the negative 2 over 2 factorial times the 3x over 2 squared plus dot dot dot. I will proceed in simplifying within each set of brackets. So we've got 3 and then 1 plus x squared plus dot 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 plus 2 times the 1 minus 3x over 2 plus 9x squared over 4 plus dot dot dot. I will further expand to get 3 plus 3x squared plus 2 minus 3x plus 9x squared over 2 plus dot dot dot, and we collect like terms together. We can see that the 3x with the negative 3x will cancel out, and we are left with 5 plus 15x squared over 2 plus dot dot dot. In II, we need to find the range of values of x for which the expansion is valid, and we know that once we reach the form of 1 plus or minus something to the power of n, then the expansion is valid for the modulus of that something being less than 1. Well, in our case, we had 1 minus x and 1 plus 3x over 2. So we can easily start by saying the expansion is valid for the modulus of x being less than 1 and the modulus of 3x over 2 being less than 1. Well, this simply means that the modulus of x is less than 2 over 3. And since we need both of these inequalities to be satisfied, we get the stricter of the two, the tightest of the two, which is the 2 over 3. And therefore, we conclude that the expansion is valid for the magnitude of x, the modulus of x, being less than 2 over 3. In question 2, we've got a set of points px, y defined parametrically here. We need to show that all points lie on a straight line. Well, starting with the two parametric equations, I will be making t the subject. So for x is t minus 1 over 2t plus 1. I will start by cross multiplying to get 2xt plus x is equal to t minus 1, leading to x plus 1 being equal to t minus 2xt. I will factor out the t on the right hand side, leading to t brackets 1 minus 2x, and therefore we arrive at x plus 1 over the 1 minus 2x is equal to t. Now for y being equal to 6 over 2t plus 1, once more I will cross multiply to get 2yt plus y is equal to 6. So 2yt is equal to 6 minus y, leading to t is 6 minus y over 2y. Well, I will combine the two because both of them are equal to t. I'm trying to show that they are lying on a straight line, so what I've got at the back of my mind is that I need to end up with the equation of a straight line involving only x and y to reach a formal conclusion. So let's equate the two. We're looking at x plus 1 over 1 minus 2x being equal to 6 minus y over 2y. I will cross multiply to get 2y brackets x plus 1 is equal to 6 minus y times 1 minus 2x. Let's expand the brackets to get 2yx plus 2y being equal to 6 minus 12x minus y plus 2xy. We immediately notice that the 2yx terms will cancel out, and this leads to 3y being equal to 6 minus 12x. I will divide everything by 3 to get y is 2 minus 4x, which I recognize as the equation of a straight line, and therefore we conclude that all points lie on a straight line. Without the conclusion here, you will be penalized with a mark. In part B, we are asked to hence or otherwise find the x-coordinate of the point of intersection of the line which is found with the line y is x plus 12. Obviously, I'm solving simultaneous equations here. So we've got 2 minus 4x being equal to x plus 12, leading to negative 10 being 5x, and therefore the x-coordinate is negative 2. In question 3, we're given a sketch of the curve with this equation. The region R is bounded by x is root 5 and x is 5, the x-axis and the curve, and we are told that this is rotated through a full revolution about the x-axis, and we need to use integration to find the exact volume of the solid generated, giving our answer in the form A, L, and B. Well, we know that the volume of revolution is given by pi times the integral of y squared dx. Well, in this case, the limits will be root 5 and 5. So let me write this down. So root 5 and 5. Well, obviously, the y squared is simply 3x over 3x squared plus 5. So it's the integral of root 5 up to 5 of 3x over 3x squared plus 5 dx. And in order to proceed in integrating 3x over 3x squared plus 5, let's recall that the integral of f dash of x over f of x is ln f of x plus c. This is called integration using standard patterns or reverse chain rule. Well, the derivative of 3x squared plus 5 is 3x, so it would be just great if I could see a 6x appearing in the numerator. So the way to achieve this is to multiply within the integral by 2, so it's the integral from root 5 up to 5 of 6x over 3x squared plus 5 dx. And to counterbalance the effect of multiplying by 2, I will divide outside by 2, so I can proceed. It's pi over 2 ln of 3x squared plus 5, with the limits being root 5 and 5 respectively. So all I have to do is substitute the upper limit and substitute the lower limit, deduct the 2, and simplify. So we're looking at pi over 2. We've got a ln of 3 times 5 squared plus 5, and then minus pi over 2 ln of 3 root 5 squared plus 5, and I will proceed. This is giving me pi over 2 ln of 80 minus pi over 2 ln of 20. Well, we know that ln of a minus ln of b is equal to ln of a over b. So this will simply give me pi over 2 ln of 80 over 20, which simplifies to give me pi over 2 ln of 4. Now recall that we need to give our answer in the form a, l, and b, where a is irrational and b is a prime number. Now obviously 4 is not a prime number, so I will write this as pi over 2 ln of 2 squared, so that the power of 2 can come down using the power law of logarithms, leading to 2 pi over 2 ln 2, which simplifies to pi ln 2. In 4a, we need to use substitution. U is root of 2x plus 1 to show that the given integral here leads to the integral from a up to b of ku squared e to the u du, with a, b, and k being constants to be found. So let's start with the substitution we've been proposed to use. It's u is equal to the square root of 2x plus 1. Well, the first thing to do is square everything to get u squared is equal to 2x plus 1. Remember that in integration by substitution, we're trying to translate everything. So let's start with the du and the dx. We're looking at 2u du being equal to 2 dx. Obviously, the 2's will cancel out. So we've got u du being equal to dx. Another thing I could do is look at the limits. Where does x being 4 take me with regards to u? So we've got that when x is 4, u is equal to 2 times 4 plus 1 square rooted, which gives an answer of 3. Whereas when x is equal to 12, we've got u is the square root of 2 times 12 plus 1. It's the square root of 25, which gives an answer of 5. And therefore, the integral of root of 8x plus 4 e to the root 2x plus 1 from 4 to 12 with respect to x can be written as the integral from 4 up to 12. I will factor out a 4 from here, so we've got root of 4 and root of 2x plus 1, and we've got e to the 2x plus 1 square rooted dx. So we know that the root of 2x plus 1 is simply the u, so I will put a u here. I will put another u here for the root of 2x plus 1, and we've got that in the place of dx. I'm going to be putting a u du, so I can do the full translation. I will also be changing the limits. So we're looking at the integral from 3 to 5 of 2, which is the square root of 4, times u times e to the u times u du, which leads to the integral from 3 up to 5 of 2u squared e to the u du. In part B, we're asked to find by algebraic integration the exact value of this integral, giving our answer in its simplest form. Well, from the previous part, we have established that this is the integral from 3 up to 5 of 2u squared e to the u du. Now, this is a standard integral that we'll be approaching through integration by parts. Now, the formula for the integration by parts involves u and v, but since u is actually my variable here with respect to which I'm integrating, let's rewrite the root for integration by parts in terms of w and v. So wv dash, their integral is given by wv minus the integral of w dash v with respect to x. So we're looking at setting w to be 2u squared and v dash to be e to the u. So we have w dash being 4u and v being the integral of e to the u, which is e to the u. So wv will be 2u squared e to the u minus the integral of 4u e to the u du. So I will apply integration by parts again here. So I will be setting this time w to be 4u and v dash to be e to the u. So w dash is 4 and v is e to the u. This means that the integral of 4u e to the u du is equal to 4u e to the u minus the integral of 4e to the u du, which gives me 4u e to the u minus 4e to the u. I'm not going to put the constant of integration here. There is no need because this is a definite integral. I will be applying the limits. So overall, we're looking at the integral from 3 to 5 of 2u squared e to the u du being equal to 2u squared e to the u minus the 4u e to the u minus 4e to the u, and the limits are 3 and 5. Before I proceed in substituting the limits, I will simplify the expression. So this is 2u squared e to the u minus 4u e to the u plus 4e to the u from 3 up to 5. Let's substitute the upper limit of 5. This gives me 2 times 5 squared e to the 5 minus 4 times 5 e to the 5 plus 4 e to the 5, and then the lower limit of 3, which is 2 times 3 squared e to the 3 minus 4 times 3 e to the 3 plus 4 e to the 3. So let's simplify things. We are looking at 50 e to the 5 minus 20 e to the 5 plus 4 e to the 5. That's the upper limit. And then for the lower limit, we're looking at 18e cubed minus 12e cubed plus 4e cubed. So all in all, we are left with 34e to the power of 5 minus 10e cubed. In question 5, we're given a sketch of the curve with this equation here, and we are asked to find dy dx in terms of x and y. Obviously, this is the question we've been expecting on implicit differentiation, so I will differentiate from left to right, applying all rules as usual. It just so happens that if I differentiate the term in y, I will put the dy dx term as well. So the derivative of y squared will be 2y dy dx, and this is going to be equal to the derivative of 2x squared, which is 4x, plus the derivative of 15x, which is 15, plus the derivative of 10y, which is 10 dy dx. I will then collect the dy dx terms on the left-hand side of this equation. So 2y dy dx minus 10 dy dx is equal to 4x plus 15. I will factor out the dy dx term. So we're looking at dy dx times 2y minus 10 is equal to 4x plus 15. And therefore dy by dx is equal to 4x plus 15, and all of it over the 2y minus 10. Now the curve is not defined for values of x in the interval pq as shown in figure 2. This is figure 2 here. We can see that when x is p and when x is q, between these two values, we've got that the function, the curve, is not defined, and we need to find the value of p and the value of q using our answer to part A or otherwise. Well, the first thing we notice that at these points here, the x is p and the x is q, the dy dx is undefined, because if you do rise over run, the overrun will simply be 0. So this simply means that if we revisit the expression we just obtained for dy dx, we need to set the denominator to be 0. So 2y minus 10 should be equal to 0. If you think about it, if you were to substitute a value for y that will make the denominator 0 and substitute this into a calculator, you get a math error which is undefined, which simply means that dy dx here is not defined. So 2y minus 10 is 0 means that 2y is equal to 10, which makes y equal to 5. So we can simply substitute into the equation of the curve, which is y squared is 2x squared plus 15x plus 10y. Let's put y is 5, leading to 5 squared is 2x squared plus 15x plus 10 times 5. This leads to 25 is 2x squared plus 15x plus 50. And therefore, we're looking at 0 being equal to 2x squared plus 15x plus 25. I will factorize this. It gives me 0 being equal to 2x plus 5 times x plus 5. So we are looking at 2x plus 5 being equal to 0, or alternatively, x plus 5 being equal to 0. So x is minus 5 over 2, or x is negative 5. Well, I can see that p is further away from the origin, so it must be the case that p is equal to negative 5 and q is equal to minus 5 over 2. In question 6, we are given the position vector of point A and point B relative to a fixed origin O. We are told that the line L passes through A and B, and we need to find the vector AB. Well, we know that to find AB, we need to do the position vector of B, which is 8, 3, negative 7, minus the position vector of A, which is 2, negative 3, 5. So 8 minus 2 is 6. 3 minus negative 3 is 6, and negative 7 minus 5 is negative 12. This is the vector AB. And then in II, to find the vector equation for the line L, I simply need one of the two position vectors to act as the position vector of the line. So I'm going to pick the point A with position vector 2, negative 3, 5, plus lambda times the direction vector, and we know that the direction of this line is simply the vector AB, so I'm going to put 6, 6, negative 12. We're then told that the point C has position vector 3, 5, 2, and P lies on L. We are additionally told that the vector CP is perpendicular to L, and we need to find the position vector of the point P. Well, it makes sense to draw a line. This is the line L. Somewhere not on the line, we've got the point C with coordinates 3, 5, 2, and there is a point P on L such that CP is perpendicular to L. So we know that this angle here is a right angle. Now we know that P being a point on the line L, it means that there is a value for lambda such that the coordinates of P are 2 plus 6 lambda, comma negative 3 plus 6 lambda, comma 5 minus 12 lambda, and the whole objective is for us to find the value of lambda. I will start by finding the vector CP. So I'll be doing P, which is 2 plus 6 lambda, minus 3 plus 6 lambda, 5 minus 12 lambda, minus the vector C, which is 3, 5, 2. This leads to 6 lambda minus 1, 6 lambda minus 8, and 3 minus 12 lambda. This is the vector CP. And we know that since CP is perpendicular to L, it must be the case that the vector CP dot the direction vector of the line, which is 6, 6, negative 12, must be 0. So we're looking at 6 lambda minus 1, 6 lambda minus 8, 3 minus 12 lambda dotted with 6, 6, negative 12. Well, we proceed by doing the I times the I, then the J times the J, and then the K times the K, and adding everything together. So we've got 6 times 6 lambda minus 1, plus 6 times 6 lambda minus 8, plus negative 12 times the 3 minus 12 lambda. Let's proceed in expanding. We've got 36 lambda minus 6, plus 36 lambda minus 48, minus 36, plus 144 lambda, which leads to 216 lambda minus 90. We know this must be 0 because we're looking at the right angle. Whenever we've got a right angle, the dot product is 0, leading to 216 lambda being equal to 90, and therefore lambda turns out to be 5 over 12. So we can proceed into substituting into the coordinates for P. So it's 2 plus 6 times 5 over 12, comma minus 3 plus 6 times 5 over 12, comma 5 minus 12 times 5 over 12. This will give me the coordinates of P. The question is asking for the position vector of the point P, so I need to give my answer in the IJK form, and therefore we conclude that OP is equal to 9 over 2 minus a half, 0, and this is the position vector of point P. In question 7, we are told that the volume capital V cubic centimeters of a spherical balloon having a radius of r centimeters is given by the formula capital V is 4 over 3 pi r cubed, and we need to find dV dr, giving our answer in its simplest form. So I will be differentiating V with respect to r. So we're looking at 4 over 3 times 3 pi r squared. Obviously, the 3 with the 3 will cancel out, leading to an answer of 4 pi r squared. We are then told that at time t seconds, the volume of the balloon is increasing according to this differential equation. Additionally, we've got that when t is 0, v is 0, and we need to solve the differential equation, arriving at capital V being 300t over 2t plus 3. So starting with the differential equation, the first thing to do is separate the variables, so we collect the v's with dv on the left-hand side and everything involving t with dt on the right-hand side. So we're looking at dv being equal to 900 times 2t plus 3 to the negative 2 dt. Then I can integrate both sides. Well, the integral of dv here simply means the integral of 1 times dv, and the integral of 1 with respect to v is simply v. And on the right-hand side, we've got 900 times 2t plus 3. I increase the power by 1, divide by the new power, and divide also by the derivative of the bracket plus a constant of integration. So we're looking at v being equal to minus 450 over 2t plus 3 plus c. I will use the fact that when t is 0, capital V is 0 to find the value of c. So we're looking at 0 is minus 450 over 2 times 0 plus 3 plus c. So we're looking at 0 is minus 150 plus c, which of course leads to c being 150. So we're looking at capital V being equal to minus 450 over 2t plus 3 plus 150. I still need to arrive at the form given here. So I will express the right-hand side over a common denominator of 2t plus 3. So we're looking at capital V being equal to minus 450 plus 150 times 2t plus 3, and everything divided by 2t plus 3. This leads to minus 450 plus 300t plus 450 over 2t plus 3. Obviously, we can see that the minus 450 with the 450 will cancel out, and this leads to 300t over the 2t plus 3 as required. In II, we are asked to find the upper limit to the volume of the balloon. So what we need to do is consider the value of V as t tends to infinity. So let me write this down. We've got t tending to infinity. So one thing we could do is go back to this expression we got here. As t goes to infinity, this part goes to 0, and therefore V goes to 150. Alternatively, we can go on the calculator. I'll be putting a really big number on my answer key. I press the equal sign, it's stored on my answer key, and I will be evaluating this expression with t being the value we just stored on the answer key. So I will do 300 ans over 2 ans plus 3. This will give me the value of v when t gets larger and larger. We can see it's 150. So we will simply say that v goes to 150, and therefore the upper limit that we were asked to find is equal to 150, and I need to include the unit is 150 cubic centimeters, otherwise I'll be penalized. In part C, we're asked to find the radius of the balloon at t is 3, giving our answer in centimeters to 3 significant figures. So we will start by substituting t is 3. So when t is 3, we know that capital V is equal to 300 times 3 over 2 times 3 plus 3. This gives an answer of 100, which is the volume of this spherical balloon. So we know that the 100 is equal to 4 over 3 pi r cubed, which was given in part A. So we proceed by dividing both sides by 4 pi over 3. So 100 over 4 pi over 3 is equal to r cubed, and I will take the third root of 100 over 4 pi over 3 to find the value of r. So if we plug this on the calculator, we get that r is equal to 2.879411 which correct to 3 significant figures is 2.88 centimeters. And in part D, we need to find the rate of increase of the radius of the balloon at t is 3, giving an answer to two significant figures. We also need to state the units of our answer, where we already know that dv dt is 900 over 2t plus 3 squared, and dv dr from part A, we found this to be 4 pi r squared. So I'm using the chain rule here. Dr by dt is equal to dr dv times dv dt. So we've got dv dr, so dr dv is simply the reciprocal of this, so it's going to be 1 over 4 pi r squared times the 900 over the 2t plus 3 squared, which is the dv dt. Now we know that t is 3 and we found r to be 2.879411 ... which means that dr dt is equal to 1 over 4 pi times this 2.879 ... squared times 900 over 2 times 3 plus 3 all squared. If we plug this on the calculator, we get an answer of 0.1066 ... which correct to two significant figures is 0.11, and it's centimeters per second. Because it's dr dt, the radius is measured in centimeters, the time in seconds, so the rate of change of the radius with respect to time is centimeters per second. In question 8, we've got the curve C described parametrically here. T varies between 0 and pi over 2. We are told that the point P with parameter T is pi over 4 lies on C as shown on the diagram. The line L is the normal to C at P, and we need to show that the equation of the normal is 8y plus 2x is equal to 17. I will start by finding expressions for the x dt and the y dt. Now, knowing that x is sine squared t, to find dx dt, I get the power down, I deduct 1 from the power times the derivative of the bracket, whereas for dy dt, we know that the derivative of tan is sec squared, so we're looking at 2 sec squared t. So we proceed with an expression for dy dx, which we know is equal to dy dt over dx dt. So we're looking at 2 sec squared t over 2 sine t cos t. I will then substitute t is pi over 4 into the expression for dy dx. This will give me the gradient of the normal. So when t is pi over 4, we are looking at 2 sec squared pi over 4 over 2 times sine of pi over 4 times cos of pi over 4. If we plug this on the calculator, we get an answer of 4, and therefore we conclude that the gradient of the normal, I will just flip and change the sign, so it's going to be minus 1 over 4. I also need to find the x and the y coordinates, so when t is pi over 4, then x is equal to sine squared of pi over 4, which gives me an answer of a half, while y is 2 tan of pi over 4, which gives an answer of 2. Now that we've got the x, the y coordinate, and the gradient of the normal, we can proceed with y minus y1 is mx minus x1. So we're looking at y minus 2 is equal to minus a quarter times x minus a half. I will expand the right hand side to get y minus 2 is equal to minus x over 4 plus 1 over 8. If I multiply throughout by 8, I get 8y minus 16 is equal to minus 2x plus 1. And I will collect the x and the y on the left hand side, leading to 8y plus 2x is equal to 17 as required. We're now told that the region S, shown shaded in figure 3, is bounded by the curve C, L, and the x-axis, and we need to use calculus to find the exact area of S. So this is the area here. We already know that the parametric equations for x and y are x is sine squared and y is 2 tan t. We know that the parameter at point P is pi over 4. We already found the coordinates of P being a half, 2, and I will be calling this point here Q. I know the equation of the line, it's 8y plus 2x is 17, so that's the point Q. So the idea is to use integration to find this part here, and then just use the fact that I'm dealing with a triangle here on the right hand side, find its area at the two areas to find the area of S. So let's start with the obvious thing that at point Q, the y coordinate is equal to 0. So I will be substituting into the equation of the normal here. So we're looking at 2x is equal to 17, and therefore x is 17 over 2. So I'll go to my diagram. Point Q here has x coordinate of 17 over 2, and this allows me to proceed with the area of the triangle. We know that the base is simply going to be the 17 over 2 minus the half times the height of 2, which is the y coordinate of point P, divided by 2. So base times height over 2, which gives an answer of 8. We then need to proceed to find the area here. It's the area under the curve. Well, we know that the area is given by the integral from 0 up to a half of y with respect to x. Notice that the 0 and the half are x values. However, we don't have y in terms of x. We've got y in terms of t. So this will be the integral of y dx dt times dt. And I need to change the x limits into t limits. Well, we know that when x is 0 here, t is 0, because if we set sine square t to be 0, we arrive at sine t is 0, and therefore t is 0. And when x is a half, we already know that t is pi over 4. So the limits here will be 0 and pi over 4. So we're looking at the integral from 0 up to pi over 4. Well, y is 2 tan t, and the x dt, we have already found this to be 2 sine t cos t dt. So I proceed. We've got that the integral from 0 up to pi over 4 of 2 tan t, 2 sine t cos t. I'll be doing 2 times 2 is 4. I'll be writing tan t as sine t over cos t times the sine t cos t dt. Obviously, the cos t with the cos t will cancel out. So we're dealing with the integral from 0 up to pi over 4 of 4 sine square t dt. Well, we know the double angle formula for cos says that the cosine of 2t is 1 minus 2 sine squared t, which means that 2 sine squared t is equal to 1 minus cos 2t. So what I will do, I will split the 4 as 2 times 2. So we're looking at 2, the integral from 0 up to pi over 4 of 2 sine squared t dt, which is of course 2 times the integral from 0 up to pi over 4 of 1 minus cos 2t dt. Now the integral of 1 is simply t. The integral of cos 2t is a half sine 2t. The limits are 0 and pi over 4. And I will proceed in substituting. If I substitute the upper limit, I get 2 times pi over 4 minus a half sine of 2 pi over 4. That's the upper limit substituted. Well, if I substitute the lower limit, this is 0 and this is also 0. So this is simply going to be a 0. So all of this simplifies to pi over 2 minus 1. This is the area under the curve between x is 0 and x is a half. So to find the shaded area, which is the area S, I simply need to add up the area we just found together with the area of the triangle. So it's pi over 2 minus 1 plus 8, which gives me an answer of pi over 2 plus 7 units squared for the area of S. In question 9, we've got a student who's been asked to prove that for p in the naturals, then if p cubed is a multiple of 3, then p must be a multiple of 3. Now the student approached this through a proof by contradiction. He assumed the negation, the opposite, so there exists a number in the naturals such that p cubed is indeed a multiple of 3, but p is not a multiple of 3. Now if p is not a multiple of 3, then it could be a multiple of 3 plus 1. And the student has shown that this is not a multiple of 3, as it is 3 times an integer plus 1. And we are asked to show the calculations and statements required to complete the proof. Now, we have started by assuming that p is not a multiple of 3, so it could be a multiple of 3 plus 1, or alternatively, we could consider p being equal to 3k minus 1, so we're saying that p is 1 less than a multiple of 3, where k belongs to the natural numbers. Then we consider p cubed, and we're trying to show that this is not a multiple of 3, so consider p cubed, which is equal to 3k minus 1 cubed, which gives an answer of 27k cubed minus 27k squared plus 9k minus 1, which leads to 3 times 9k cubed minus 9k squared plus 3k minus 1, which is not a multiple of 3, and therefore we've got a contradiction. Hence, p cannot be of the form 3k plus 1 or 3k minus 1, and therefore we conclude that if p cubed is a multiple of 3, then p must be a multiple of 3 as well. Now, alternatively, instead of p being 3k minus 1, you could have considered p is 3k plus 2, which should again lead to the conclusion that this is not a multiple of 3. In part B, we are asked to hence prove by contradiction that the third root of 3 is an irrational number. So the proposition is there, the third root of 3 is irrational, and with contradiction we always start by assuming the opposite. So we say suppose not, i.e. the third root of 3 is rational. This simply means that it can be written as the ratio of two integers, and I will say that these integers have no common factors, so we have started with a simplified fraction. I will proceed by raising everything to the power of 3, leading to 3 being equal to a cubed over b cubed. I will cross multiply to get 3b cubed is equal to a cubed. And since the left-hand side is a multiple of 3, it means that a cubed is also a multiple of 3, and therefore with the result from part A, we conclude that a is a multiple of 3, and I will set a to be equal to 3c. This means we're looking at 3b cubed is equal to 3c all cubed, so we're looking at 3b cubed being equal to 27c cubed, and therefore b cubed is equal to 9c cubed. Again, we observe that the right-hand side is a multiple of 3, and therefore b cubed is a multiple of 3, which means that b is also a multiple of 3, which is obviously a contradiction because we have started with a and b having no common factors, and yet we are concluding that both are multiples of 3. Therefore, we conclude that the third root of 3 is indeed irrational.